Processed materials form an essential part of our everyday lives. From the water we drink, which has to be filtered or desalinated if we are purifying seawater, to the food we eat. The food is often processed and manufactured and converted into different forms. And even the food that we grow requires fertilizers, which has to be processed and which has to be synthesized in chemical processes. The house we live in requires cement, which once again has to be processed by combining limestone, clay, and sand in order to give the strength that is required. The steel that has to be purified, molten, and then in blast furnaces, and then converted into steel rods. And different applications such as personal care, food, different industries require us to process materials. This materials processing is often done in reactors at large scales. And this is because we have to find ways that are repeatable, reproducible ways of processing so that the product is the same every time. It has to be economical, it has to be energy efficient, and it has to be environmentally friendly. These are the requirements for processing materials. How do we do these processes efficiently? Typically, these processes involve material transformations, either physical transformations such as melting or heating or cooling, filtration and so on, or chemical transformations. These transformations require the motion of materials relative to each other. For example, when you filter water, you require the water to move relative to the impurities. These require heat, for example, for heating of liquids or removing heat in the case of exothermic reactions, adding heat in the case of endothermic reactions, and so on. All of these processes also require forces to be applied, for example, in mixing, in stirring, and so on. These processes, in order to be done efficiently, what are the basic principles that are used? That will be the subject of this course. Welcome to this course on Advanced Transport Processes. My name is V. Kumaran and I am at the Department of Chemical Engineering at the Indian Institute of Science. As the name indicates, this is an advanced course. I require you to have familiarity with basic transport processes, which was part of another NPTEL course, which you should have completed earlier. So, in this course, we will deal with application of mathematics for first deriving equations for transport processes and then solving those equations in different ways in order to be able to predict how transport processes occur. For example, if you have a chemical reactor, for example, and it's a heterogeneous reaction with catalyst particles and a stirrer, for example, the reaction takes place on the catalyst surface. Therefore, reactants had to be transported to the catalyst surface, and the system has to be engineered such that there are concentration differences that transport this reactor to the catalyst surface. Similarly, the product has to be removed from the catalyst surface, and therefore there has to be a difference in concentration between the surface and the bulk of the fluid. There may also be the requirement for heat transfer if the reaction is exothermic or endothermic, and the reactor typically has to be stirred to enhance the rates at which materials are transported to and from the catalyst surface. The rate of transport of these materials based upon the differences in concentration, temperature, and so on will be the subject of this course. In the basic course, you would have learned the fundamentals of dimensional analysis, of the reduction of a problem expressed in dimensional parameters to a problem expressed in dimensionless groups, and correlations between these dimensionless groups. We would also have derived the constitutive relations, the Fourier's law for heat transfer, Fick's law for mass transfer, and Newton's law for momentum transfer in that class. And we had solved using shell balances. We had derived the equations in one dimension. and we had looked at how the equations can be solved at steady state, and we had also done some modeling of entire reactors and so on using these transport processes. If you recall, the textbook that you had used was the textbook on fundamentals of transport processes, which was the basic textbook for the basic course. The same textbook will be continued for this advanced course. Here we will look at derivation of the conservation equations for heat, mass and momentum transfer in 3 dimensions in general and in different coordinate systems. So for example, if you have a plane surface, it is you can use a Cartesian coordinate system. But if you have transferred to a spherical catalyst particle, it is preferable to use a coordinate system in which the surface of the particle is a surface of constant coordinate. So we will derive the equations for different coordinate systems and show you how we can do a general derivation. After that, we will look at transient processes where the transport takes place in both time and in the spatial coordinates. And after that, we will go to 2 different types of transport in 2 limiting cases. The first, where diffusion is dominant, and the second, where convection is dominant. Recall that molecular diffusion is a process where, due to the molecular fluctuating velocities of the molecules, there is transport when there is a variation in concentration for mass transfer, a variation in temperature for heat transfer, or a variation in momentum for momentum transfer. These constitutive relations will be used in order to derive the rates at which transfer takes place in simple configurations. Then we will go to the limit where diffusion is dominant so that we can neglect convection altogether and look at ways to solve these problems. The second is where convection is dominant, and here, even though it appears that diffusion can be neglected, it turns out that you cannot simply neglect diffusion because transfer to a surface ultimately has to take place due to diffusion. So these are cases of diffusion, convection dominated transport, both due to forced convection as well as due to natural convection. And we will look at these cases as well. And in between, we will also look at some problems in momentum transfer. So that will be the broad outline of this course that we will be going through together. So I welcome you to this journey of learning, and I urge you to look at the textbook also, because I will be referring to specific sections as I go through the lectures. And together with the textbook and the notes, I hope you will be able to get a good appreciation of the importance of transport processes, how they can be applied, and you will be able to actually appreciate why systems are the way they are in both natural processes as well as in industrial processes. So welcome again, and let's go progress on our journey.